Okay, can I get your attention? Today is going to be our fourth talk of the semester, and we're lucky enough to have Dr. David Talent with us. Now, Dr. Talent, he, I can't go through his entire resume because there's not really enough time in the talk, but he has, let's say he was faculty member for several years before he came to NASA JSC. He's an astronomer. I believe all his degrees are in astronomy, and he's also been adjuncting at UHCL for about 10 years.
Well, actually, since about 76, with a break while I was in Hawaii.
Yeah.
So 10 years during the last.
10 years in the last stretch, but several years before that. And also another thing is that he has advised a lot of students, not just in the classroom work, but also in independent research projects and a lot of special projects outside of the classroom. So he's, and on top of that, out of most of the faculty we've had, he is one of the few who has gotten consistently nearly perfect teaching evaluations in pretty much everything he's taught. So he knows how to work with an audience. So with that, I'll turn over to Dr. Talent.
Thank you for that very kind, glowing introduction. Two things I want to say up front. Like a klutz, I forgot to wear my hearing aids. So when we get to a part where questions, etc., are appropriate, you may find it necessary to speak up a bit, and I may even find it necessary to have the question repeated. Sorry for that little inconvenience. Also, because people notice it and never know what to say, notice the relative steadiness of the laser here, relative. And that's as good as I can do it over there. This hand wanders all over the place and does its own thing, so don't let that throw you. I had, in fact, one student once called me Dr. Strangelove in reference to a 1962 black and white film, which some of you may have seen, and those of you who haven't really should rent it and take a look at it. It's excellent. Dr. Strangelove, or How I Learned to Stop Worrying and Love the Bomb. George C. Scott. Anyway, my background, my undergraduate work was in physics. My master's and PhD in space physics and astronomy from Rice University, where I did studies of the chemical abundance characteristics of H2 regions. That's why I put the picture of the Milky Way in here. It has nothing to do with the talk. It's just that I'm an astronomer, so I got to have some star pictures in there somewhere. And there are H2 regions here at a few locations, and those are the kind of things that I always studied and enjoyed. So anyway, there you have it. But the topic for this evening has to do with a prioritization methodology for orbital debris removal. A few months back, the Defense Advanced Research Project Agency and NASA held a workshop in Virginia to discuss the possibility of removing large orbital debris elements to try to reduce the likelihood that the space environment will eventually become so cluttered, so trashed out, that normal operations, in fact, may not be possible. As some of you, in fact, I actually see a few people here who I would imagine do recall, October of 1957. How many people actually recall October of 1957? Yeah, a few people. Sputnik was launched. I was 5 years old at the time, but I was aware that all the adults in the neighborhood kept gathering out in the front yards in the evenings to watch something in the sky. And there was something about bombs from above, the high ground, commies in space, that sort of thing. There was a lot of fear and trembling because the Russians had beat us into orbit, and people watched the Sputnik pass over. Actually, what they were watching most of the time was the booster that put Sputnik into orbit. The Sputnik satellite, or as the Russians would say, Sputnik, itself was actually only barely visible to the naked eye. The rocket body that put it there was actually much more pronounced, and most people who saw something actually saw that. That was the first, in fact, piece of orbital debris. From 1957 to this date, human beings have had a tendency to trash out space. Big surprise. Like we do everything else. Oh, look, the national parks. Oh, one beer can will make any difference. You know, so you have that sort of thing. We have, for a long time, people tended to operate, that could be very dangerous with this, people tended to operate with the big sky theorem at their disposal. The idea that space is big, what's the chance that a couple of pieces of stuff that we put up there are going to bump into each other? Well, in fact, in 1978, the first paper predicting the possibility of significant orbital debris growth due to eventually not just the deposition of material into space, but the actual, as a result of or consequence of collisions, that paper was written by Don Kessler and Burton Kerpole at NASA JSC. It was met with some interest, but mostly a lot of skepticism, especially on the part of the military and some commercial space interests who, again, took the attitude that, hey, really seriously, space is big. You're not going to be banging into each other up there. You've got plenty of room. Well, it turns out not to be the case. I'm hoping that the arrows advance this.
Yeah.
Here we go. The problem is on-orbit collisions. What you're looking at here is a graphic, or a couple of graphics produced by AGI, the folks that have built and distribute Satellite Toolkit, a really excellent multi-use satellite modeling system. But this is from actual data after the collision of Iridium 33 and Cosmos 2251 back in February of 2009. These two objects, both of them payloads, one of them non-operational, the Cosmos, and the other one actually an operational system, operational satellite, collided. And instead of two easily tracked pieces of stuff, you end up with hundreds of pieces of debris that are trackable, and God only knows how many pieces of debris that are not trackable, all of which are dangerous. Not only does it trash out the altitude at which the collision took place, but you can see from this diagram, which is called a Gabbard diagram, that pieces of debris have been thrown into high orbits. And so the event that took place at one altitude manages to make a mess that can be felt throughout the environment. Just in case you haven't seen a Gabbard diagram before, what this is for each individual piece that has been tracked, you plot the apogee and perigee against, what have they done in this case? The altitude in kilometers. And you can see that some stuff has been kicked into higher orbits, some has been kicked into lower orbits. That is where at the collision altitude, some objects now have that altitude as their perigee with a higher apogee. Some objects now have that altitude as their apogee with a lower altitude as their perigee. Of course, the nice thing about the stuff that goes into this half of the diagram, at least it has a chance of decaying quicker. The stuff up on this side that's been kicked primarily into higher orbits will be there for quite a while, depending upon the altitude at which the collision took place and all of that sort of thing, and the characteristics of the pieces. This particular presentation is one that I presented at the meeting in Virginia, the DARPA and NASA co-sponsored meeting. They're trying to get some ideas together, and then they're going to put out a solicitation. Oh boy, money, 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 for whoever wins the solicitation and gets a good proposal in. We hope we do, but who knows. So a bunch of people from all over the world, about over 100 representatives of different companies, government agencies, and even foreign interests showed up, and a number of us gave papers. This is the presentation I gave. Basically, let's just kind of walk through it. The objective of this particular work was to develop a prioritization methodology for orbital debris removal. What do? Go after the small stuff? Go after the big stuff? Go after the high stuff, the low stuff in the most crowded areas? what do you go after first? What's the logic? The particular approach that I took is based on a model that I developed and published in 1992 called the particle in box model. It's a debris environment evolution model. A number of people have prepared debris environment evolution models. NASA has several models. They have a Monte Carlo model called, well, the previous one was Evolve. I think the current version is called Legend. Someone can correct me if you know different. The Europeans have their models, that sort of thing. Most of these models are very calculationally intensive, especially the ones that are basically Monte Carlo type of models where you have to run it kind of, 100 times and then kind of take the average characteristics to see what's going to be happening in the next 30, 40, 50 years. But the particle in box model is a fairly simple model, and the discussion that we're going to follow here is we're going to first of all review the structure of the single particle equivalent particle in box model, which most of you probably have never heard of in the first place anyway, so it's not really a review, it's more of a preview or intro. We're going to also look at the requirements for environmental stability against catastrophic collisional cascade. We're going to take a look at a couple of cases. The first case will be long-term evolution illustrated, where no targets, no objects are removed. We just do the same dumb thing we've been doing forever, putting more and more junk in space. And we watch and see what the model predicts in terms of behavior, in terms of the trashing out of the environment. Then we're going to take a look at the current LEO population and just get some idea of the range of characteristics for large and small objects. Then we'll take a look at a second case, long-term evolution illustrated with target removal. What if you strategically remove a few objects, not many, but you focus on a particular end of the size spectrum, take out the big ones? How does that change the predictions for the evolution of the environment in terms of how quickly it becomes trashed out and whether it becomes critical? What I'll also then follow along with is presentation of the collision rate equation for objects of different sizes, and discuss the methodology that I've come up with here for prioritization for the removal of these objects. If you have a certain budget available to you, which ones do you remove first? Okay. The particle in box model that I developed, first of all, this slide was because everybody has to tip their hat to Kessler and Kerpelay at these presentations, so I made sure I did that here. Okay, it's politically correct, right? So it's a good thing to do. But in 1988, inspired in part by the work of Kessler and Kerpelay, which I really was, the author of this presentation, myself, I set out to develop a debris environment model based on a simple differential equation, taking an approach that was thermodynamic in character, and I'll explain that in a little more detail. Originally it was presented in 1990, and it was published in 1992. A little bit of tiny tweak of background on how this model got started. In 1988, 2 years after I started working for Lockheed Martin supporting the SEAT contract at JSC in the orbital debris group, several of us had the opportunity to go to the Pentagon and do a presentation for the Strategic Defense Initiative Survivability Office. They had an office dedicated to looking at the survivability of the systems that they were talking about putting on orbit at that time. Anyway, a group of us went in, we did this presentation. It was largely based on the projections of the Evolve model, which is a multi-thousand line model, and was written by dozens of people, some of whom no longer worked at JSC at the time. Anyway, it was this big model that predicted that under certain scenarios, some of the things that the military was thinking about doing might not be a necessarily good idea. I was sitting in the back of the room, and there was a gentleman sitting there next to me who was a major. He was essentially our sponsor for this meeting, or at least our watchdog, whatever you want to refer to him as. Anyway, he was sitting at the back of the room. He wasn't feeling too well that day, as I recall. And he leaned over to me, and he was listening to one of the presentations, and he leaned over and he said, "You know, I don't trust you. I don't trust the people you work for. And God knows I don't trust NASA. You're here telling us that all this stuff we're going to do is going to cause some kind of trash out of space." He said, "This program that you guys have run is thousands of lines long. You've got people that have written parts of it. You can't even get in touch with them anymore, or they're retired or dead. How can I believe this? How do I know there's not a couple of lines of code in there that twist this whole thing in the direction that you guys are presenting? He said, I'd like to see 300 lines of Fortran code that maybe have simplifying assumptions that at least would confirm what you guys are telling me. That I took as kind of a challenge. I went back to my hotel room that evening and began to work on a very simplified model for the environmental evolution of orbital debris. There are two key elements to the approach to this model that I developed. One was to treat the entire LEO environment as though it were a box with global average characteristics. The environment isn't really that way, but that's the way I treated it. Because one of the first things you do when you make simple models is you abandon reality and then later claim that the things that you abandoned are not really that significant and that the results are profound. As in, assume a horse is a sphere. You know, that kind of thing. Okay, so we described all the, and also the second key assumption was describe all the objects in the LEO environment in terms of one equivalent particle whose characteristics are determined by the total number of objects, total cross-sectional area, and total mass on orbit at any given moment. So basically I added up all the number of objects being tracked, added up all the mass in orbit, added up all the cross-sectional area, and used that to define an equivalent particle in the environment. Then the way the model works is you run it through an iteration, collisions take place, new materials deposited on orbit, etc., and you then recalculate the average characteristics with each time step. We'll see a little more about how that works in a minute. The first thing I needed to do was establish what was going to be my state parameter. You know, in thermodynamics you can have intensive variables like temperature, or extensive variables like volume, density, energy, things of that nature. I chose for my state variable the number of objects. N, the number of objects resident in the LEO environment at any given time. The reason I chose that was because if an object can be seen, it can be counted. The number of objects on orbit is a direct observable, of course subject to the limitations of observation. You have to appreciate the possibility of incompleteness in your counting as you go to smaller sizes and higher altitudes. The basic particle and box equation describing the change in the LEO population with time is presented here as n dot equals a plus bn plus cn squared, and we'll look at where some of these terms came from. The simplest, when I went back to the hotel that evening after this de facto challenge put forth by Major whatever his name was, I asked myself, what's the simplest possible model I could come up with for the environment? And it was dN by dt equals 0. Because when you integrate that, you get a constant. And what's that constant? It's the number of objects in orbit right this minute, maybe for the next 10 or 15 seconds, or maybe the next day or so. It's a pretty good model. In fact, if you go to Celesttrack, the website, or one of the Air Force sites where they publish this type of data, there's a quantity called the box score. Basically what I had derived was a simple model that gave as its answer the box score. Of course you had to know the answer when you did the integration, so it wasn't much of a model. Well, that's simple, but it's not very illuminating. N dot equals 0. So the first thing I thought of was, well, we actually put objects into orbit at some rate. So I'll let the deposition term be this quantity I called A. So now we have a slightly more sophisticated model, N dot equals A. So you can have an initial value plus some growth. Or if you start removing objects instead, a term that takes them out. But objects do decay due to the residual atmosphere at altitude. More efficiently at lower altitudes than higher altitudes, but we're dealing with this homogenized box here. And the number, the probability per unit time for any given object I took to be this quantity B. So now we have the second term, Bn. Now the production of fragments during collisions is the quantity C. Between members of a population may be developed in a fashion after collisions between particles in a gas. If you look at Halliday-Resnick, you know, the old text I used, where there's, in fact, pick up the double volume of it, flip to the back, look up mean free path, flip to page 500 and whatever it is. And you'll see a description that points out the fact that collisional processes between objects that are bouncing around in a box proportional to the number of objects squared. That's where this term came from. So now I was left with the task of coming up with a description of each one of these terms. Now, this model is a model that I call Phenomenological Model. Basically, the construction of the model appeals to the phenomena itself. In other words, you ask yourself, what are the things that are going on? And can I use the things that are going on to actually help me build the numerical values for some of the coefficients, if not all of them? Well, the deposition term must involve the number of launches per year worldwide. And of course, with any given launch, there's a certain number of pieces put up. There's the object you intend to orbit. Oftentimes there's a rocket body, maybe a couple of fairings or cones or bands or things that hold the stack together. So the average number of pieces per launch I call P1. But I decided that you don't want to count everything. I mean, if some stuff only stays up for two revs, it's really not part of the environment long enough to be of significance. So I decided to come up with a fraction of P1 that meets the membership conditions, which I basically said was a year or more at an altitude of 300 kilometers or higher. Kind of arbitrary, but I had some justifications for it at the time. Now, of all these things that are launched, a fraction of the launches eventually result in an on-orbit non-collisional fragmentation. There have been well over 150, I'm not sure what the exact number is now as of this date, rocket bodies simply blowing up. There were some particular upper stages that were well known for that. I think the Delta upper stage that had a common bulkhead between the fuel and oxidizer. And these were hypergolic fuels, so that what happened is that if the common bulkhead ruptured, whatever was left blew the thing to pieces. So there were a number of objects that simply blew apart. Actually, about 3% of all launches up until about 10, 15 years ago would produce some type of eventual fragmentation on orbit. So we have some FCB, some fraction of launches resulting in on-orbit non-collisional fragmentation. PE was the number of fragments produced per explosion. I went back to historical records to try to get some kind of ballpark number for that. DE was the fraction of PE meeting the membership conditions again. And then also I came up with the idea that in terms of deposition, you could have negative deposition, a removal term, like going up and picking up LDEF, which was actually done. So this was the A term. The B term this is the only sink term. The first term there was a source term. This is a sink term. B atmosphere is the reduction fraction per year due to natural drag. And also, one thing that's interesting is that if you consider the average piece of debris to be something like a sphere, the mass goes as r cubed. The cross-sectional area goes as r squared. So the area to mass ratio goes as 1 over r. What that means is smaller pieces of debris, for at least a homogeneous sample of objects, smaller pieces of debris, in fact, are more strongly coupled to the atmosphere. The small stuff with large area to mass ratios tends to come out of orbit quicker. So as the average characteristic particle changes in the model, the rate at which things are taken out is going to change as well. Now, another thing you could do, rather than just sitting around waiting for the atmosphere to clean the mess up, is build some kind of a sweeper. And in this particular example, I allowed the debris sweeper to have characteristics that with some particular efficiency, it swept out some value of some fraction of the population per year. So you could or could not invoke that in any given model run if you wished. Now, for the collision coefficient, the production term is a product of two quantities. One is the number of fragments produced per collision minus the two that are destroyed in the collision. So you have two bowling balls hit each other. You lose two big bowling balls, but you gain a whole lot of bowling ball fragments. All right? Now, H dot sub 1,1 is the collision frequency between members of a population of identical objects. And we present that explicitly in the next slide. This is where the thermodynamic assumption comes in. F sub nu is what I call the incomplete mixing factor. All the stuff that you see in the brackets and the parentheses comes straight out of a simple thermodynamic type of model. The F sub nu quantity is an empirical quantity thrown in to allow for the fact that in fact any given object in Earth orbit does not in fact have access to all parts of the environment. It's constrained by the fact that it is in orbit. It's in a given plane, it's in a given inclination, it's in a given altitude range defined by its eccentricity. It's not really a particle bouncing around at random. The other quantities are defined. V sub c is the orbital speed for an average particle of population, d1 the average population object diameter, n1 the number of objects having that diameter, RT and R sub b are the radius at the top and the bottom of the environment from the Earth's center. So that defines the volume in which all these objects are interacting. Now, just for a moment, we don't bother trying to solve the equation itself. We take a look here at some of the implications of just the form of the equation. The PIB model actually allows for an examination of whether or not the environment is stable. What I mean by stability is simply this. If you have objects orbiting the Earth in the low Earth orbit environment and a collision takes place, does that collision tip the environment over the edge and cause a catastrophic runaway of collision after collision after collision after collision after collision? Or is the environment robust enough to recover from that collision and not proceed to a runaway condition? It turns out that you can examine that by looking at the relative magnitude of the various coefficients of the population environment equation. It has the form of a simple quadratic. And yes, it is over 2c, not 2b, because I used the coefficient A and B and C a little bit differently than they're usually used. Somebody pointed that out once, and I thought, when I was actually doing a presentation in front of a large group of people who were like, you know, the kind of people that write checks for research, they said, "Oh, you've got the wrong term in the bottom." And I thought, oh crap. But it's because I switched my B's and my C's. Anyway, by constructing the equation you see here, by application of the quadratic formula, you can intercompare the relative effects of the deposition, the removal, and the collision terms. Take a look at that for just a second. Minus b plus or minus under the radical square root of b squared minus 4ac over 2c. In particular, focus on the quantity under the radical. Q is equal to b squared minus 4ac. Well, what is b squared all about? It's about sinks. What's 4ac all about? It's about sources. And the behavior of that formula is dependent upon whether or not that quantity Q is greater than 0, sinks greater than sources, in which case if sinks are greater than sources, the environment is conditionally stable. It has two real roots when you solve that expression. If Q is equal to 0, the sinks and sources are equal, the environment is on this instability threshold, it only has one real root. If Q is less than 0, sinks are less than sources, sources are dominating the environment, it's unconditionally unstable, the environment is in a condition of runaway until something happens to arrest it. Now here we actually consider an example case where I put some real numbers in and crunched it, and we see the expression where in this case we have two real roots, n1 equal 120,000, n2 equals 490,000 for the particular set of coefficients that were used in this example. In this example we have conditionally stable behavior. The number of objects in Leo, n, might be some value below n1. What's going to happen is that as time passes it will approach, as long as it's not disturbed to the point that the number of particles in the environment suddenly increases beyond n2, what will happen is that the environment will decay back to n1. So for example, suppose you're sitting there at 50,000 objects on orbit in this example, and you suddenly put another 150,000 up due to maybe space warfare. Everybody's blowing up each other's satellites. And it's up to about 200,000. Notice that the curve goes below zero as you look at the dn by dt axis. In other words, you get a boost in the number, but then it decays and asymptotically approaches n1. The environment is stable. What if you ended up with such a scenario that you suddenly push the environment beyond n2? dn by dt is positive, and it's predicting that the environment runs away. Now, of course, the shape of this curve is not static. With each time step or with each change in the environment, you have to reevaluate it. And so what happens is, if you could make a movie of this, which I ought to do sometime, you would see that at each time step, this parabola is changing, maybe from stable to becoming unstable. The environment runs away, the particles mulch themselves up, then they're removed more efficiently. The environment then again becomes more stable, catastrophically approaching a new equilibrium, which is not necessarily desirable, although it is an equilibrium case. Now, we'll linger on this for just a little bit. This is the PIB model illustrated for long-term evolution with no large object removal. Now, I say here using nominal parameters. I have a list of those in a backup slide if anybody's interested, but the numbers that actually went into the model. You can take a look at my 1992 paper. In fact, if you'd like to, you can reference it in some of your own scholarly work, which will boost up my citation number. And never mind. Here's the situation we have. Now, the assumption here is, now notice that this goes out for 5,000 years. Okay? You do that kind of stuff when you run a model, and I just put the numbers in. I want to see how the model behaves. And what we're assuming here is that a certain launch rate's going on, a certain explosion rate's going on, and that no effort's being done whatsoever to do anything corrective. Just humankind just keeps blindly doing everything the way they've been doing it, and they do it for a couple of thousand years. I mean, obviously that's not going to happen, but it illustrates the behavior of the model. What happens is that currently the environment is unstable and does not exhibit two real roots until the year 2400. By the way, this is borne out by other people's models. The low Earth orbit environment, even if we stop launching stuff right now, will continue to grow in number. The current low Earth orbit environment is unstable by everybody's reckoning. Everybody who does this has been getting the same answers. It's kind of we're watching a slow, almost like watching a nuclear reaction in slow motion. It's already to the runaway point, and it's proceeding. Okay, the LEO debris growth may be expected to continue until the year 2590 in this model, because the total population will continue to be greater than N2, as we saw in the last in that presentation of the roots. Throughout the growth period, the average object size will get smaller, the graph at the bottom, because what's happening, you're beginning to mulch objects up by going through more and more collisions. You've got fewer and fewer intact objects, you've got more debris pieces. As the average particle size diminishes, the efficacy of atmospheric drag increases. N1 will become smaller than N2, will become smaller, and N2 will become larger. The parabola will open up, grab the point where the state of the environment currently is, and then it begins to decay back, and that's why it reaches a peak and turns over. And the population reaches a peak in about 2590 and begins to decay. Eventually, a stable environment is achieved at about 795,000 objects, and that's an important distinction. Stability and desirability are not the same thing. You can have a stable, desirable environment. You can also have a stable, undesirable environment. What makes it undesirable is with that many pieces still resident on orbit, the average time between collisions becomes comparable to a typical operational lifetime for a satellite. When the average time between collisions becomes less than or equal to the operational lifetime, that basically says you're killing your satellites before they end their useful life. It becomes expensive. Yes?
What are you assuming is the average lifetime of a space system?
Well, that would be on the, probably, these days, anywhere between 5 to 15 years, depending upon the system, what it was designed for. But if you take a look at operational systems, it typically runs something like that. It's ballparkish. Okay, but this is with no attempt whatsoever. We'll revisit this shortly. Let's take a look at the current environment. We take a look at it here. In November 2009, I took a look at the radar cross-section catalog as provided to me by the folks at Celestrac. It's not actually published at their website, but they were able to redistribute it to me from their Air Force sources. And I took, for the moment, since we're just looking at LEO, the low Earth orbit environment, that objects that were resident and or transient in an altitude regime below 2,000 kilometers, I wanted to see what those objects looked like, where all the collision cross-section was, and that sort of thing. The number of objects identified were 12,619 that had reported RCS values. The total RCS of the population was 16,122 square meters. These are radar cross-sections, which have some correlation with physical cross-section until you get down to objects that are commensurate with the size of the radar wavelength. Then you get into some weird scattering phenomena, which you can't really believe the RCS represents anything physical in terms of the real physical cross-section, but when you don't have anything else, you go with what you got. The average characteristics per piece were about an area of 1.2 meters squared, a diameter of about 1.27. So, where is the collisional cross-section found? 10% of the target area is found in just 1/3 of 1% of the biggest objects. If you take the 126 largest objects, 1% of the LEO population, 22% of the target area is found there. If you take the top 10% of the population, almost 80%. So the top 10% by number, in the 1,262 biggest objects, you have like 80% of the target area. If you go back to the collisional term, the target area is a very important part of that calculation. So in other words, what do you want? If you want to build a system that's going to get hit, you do two things. You make it big, and you make it stay up for a long time. Oh, that's space station. Well, there's a third thing. You make it big, you make it stay up for a long time, and you put it in a regime of the altitude stratum, at an altitude stratum where there's a huge density of objects. Fortunately for space station, it's flying below the worst of the stuff. That's one reason that they don't have to maneuver more than they do. And they do have to maneuver some to avoid getting hit. But this is an important point. Since cross-sectional area is important in terms of being collisional effects, this suggests that if you just make an effort to remove a few of the largest targets, you could have a significant influence on the environment. Now, here are some typical cross-sections. There was no strategy to this other than just kind of randomly selecting from the catalog. Large object cross-sections, specific object types. In the upper fraction, the upper half of this, I have rocket bodies. And the typical rocket body is, when you look at the rocket body averages, typical rocket body presents about 20 square meters of cross-section. Now, debris pieces, the small stuff, Ariane debris, Sybers debris, Cosmos, yada 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 debris, typical cross-section is like 0.06, 0.07 square meters. So, if you want to invest in some type of on-orbit system, I'm not saying you shouldn't go after the small debris. There may be some circumstances where that makes some sense. But once something's been fragmented, it's almost a done deal, in my opinion. What you really want to do is go after the big stuff that's still up there, still intact, and represents a reservoir of future target area, which will just eventually become a lot of small pieces and really trash out the environment. Now, here is the PIB model, again, exercised, but we took, with the previous case shown, okay, as no removal, Okay, just let the environment run. Start with the real environment, anticipate a launch rate, run with it and see what develops. We saw that it got to be a huge number. It was unstable. It came back down. In this case, the second case, what I did was in the model I removed 2 rocket bodies a month from the environment. This is what I presented at the DARPA NASA conference. I was suggesting that if you focus on the large stuff and remove 2 typically 20 square meter rocket bodies or equivalent per month, it can mean all the difference between catastrophic runaway or relative benign growth, as you see in the lower presentation in the graph. So the question then becomes, if removing the large debris is a good thing to do because it represents most of your future collisions, and you only have a certain amount of money per year to execute such activities, where do you start? What do you go after first? So the next task is to develop a prioritization list with the objective of removing those objects that are the greatest threat from a future collision perspective. Now, this is where we look at not objects of the same type, but we look at objects of different types, different sizes. When I originally developed this model, I was trying to avoid having to deal with individual objects. That was the whole point. That was why the models that other people ran were calculationally intensive, because they did all this bookkeeping on thousands and thousands of objects and their orbital characteristics. I didn't even stop and think about it until a few months ago that if I looked at my model a slightly different way, I actually could say something about individual objects that was probably fairly relevant. During the development of the multi-particle type model, from the modeling protocol of the original PIB model, I developed a mathematical protocol for extending the PIB model. See, originally the particle box model was just took the environment as a single box, everything's rattling around inside, you watch what happens. Well, to make it a little more realistic, it seemed like it would be worthwhile to divide the environment up into, like, let's say 10 strata, divide the objects up into maybe 5 or 6 different particle or object types, look at the behavior within each strata, and then develop cross-feed terms between the different strata so that when objects dragged out of one stratum into another, you could account for it that way. When an object blew up, you could account for the objects that were thrown into higher and lower strata. And that made it a little more realistic. The formulation was a direct extension of the particle and box model, and that's shown here. And where you have to sum over every object, all the possible collisions between object types. So basically, rather than considering each object to be its own category, I divided the environment up into different types. I've got a backup slide on that. But so if you take 2 dissimilar objects, the formula looks a lot, very much the same, with the exception of, terribly afraid of blinding somebody, this term right here. The combined cross-sectional area is di plus dj divided by 2, that quantity squared, instead of just the single equivalent object that we had earlier. Now, this holds at its root the possibility of doing something kind of interesting. I can take the orbital element sets that I download from Celestrak or the Air Force website. I can sort all those out. I can compare them with their cross-sectional areas from the radar cross-section catalog, and for that matter sort them by size if I wish. And then I can ask a question. Pick any object. Pick any object in the list. And then ask yourself, what's the probability that that object is going to be, what's the mean life between collisions for that object with any other object in the population? Here's the way it works. The procedural steps. You let object 1 be the largest member of the population. You don't have to, but that's the way I chose to do it. Calculate the collision rate between that object and some other object, H12, the second object on the list. Repeat that calculation for every object in the environment, the third, the fourth, the fifth, and so on. Even if there's 13,000 of them, you can do that. Sum over the entire population to assess the risk associated with this particular object. For example, if this object of interest is right in the thick of it, where everything else is, got a pretty good chance of hitting something. If, however, it's way out at the edge of the low Earth orbit environment, there's nothing else out there in that neighborhood, it's in the boondocks, not much chance of it hitting anything else. And so for every single object, the idea is to repeat this calculation for every object in the population, and each object can then be ranked in order of relative threat to the environment. Another thing you can do, you can also do some weighting tricks. Like one of the things that's useful to do is weight each calculation by the mass of the object that you're looking at. So for example, a small object that could be involved in a lot of collisions, it's kind of unfortunate, but a large object that could be involved in the same number of collisions could be catastrophic. So that's why you might want to actually weight this calculation by the mass of the colliding elements. But in this case, all I'm looking at is the collision rate. Each object can then be ranked in order of relative threat to the environment, and the information generated by this analysis will allow for the selection of debris targets for removal, achieving the maximum benefit per unit cost. In other words, I don't want to go, if I can only remove 24 objects this year from the environment, I want to remove the ones that do the most good as quick as possible. I don't want to grab something just because it was easy and turns out that it wasn't really very important to take that object out of the environment. So when I actually performed this calculation, treating every object in the environment, payloads, rocket bodies, pieces of debris, just treating them all like debris. Here's the calculation that I came up with. This was the list. This list is actually 13,000 elements long. You're just looking at the top end of it. Meteor M, with a cross-section of about 80 square meters, showed a collision rate of what you see there in terms of number of hits per year. When you take the inverse of that, that's the mean time between collisions of about 1,000 years for that particular object. But when you start looking at if you start looking at how many collisions you would expect between any member of the population and the other member of the population, you end up getting numbers like 1 every 5 or 6 years now. Okay, so which is a little creepy. It's just, this is the same kind of thing. You can't say which one of these is going to really get clobbered first. But you can say statistically which ones represent the most threat overall. It's like if you have a room filled with 1,000 people and you've got an actuary from an insurance company, and you ask the actuary, how many people in this audience are going to die this year? You say, well, let's see, we've got a population of people here ages 20 to 80, 94% of them drive their own vehicles, etc., etc. You can look it up in the table, say 6 people in this room will be dead by this time next year. And it's probably pretty close, because that's how insurance companies make their money. But if you ask him which 6, don't know, have no idea. But I know from this population, 6 of them are going to be pushing up daisies this time next year. It's the same thing here. Just because Meteor M is at the top doesn't mean it's going to get clobbered. Just because Iridium 86 is second to the top doesn't mean it's just a little bit less at risk personally. But from the perspective of the population as a whole, this kind of gives you an idea of what you might want to go after. Now, the next step was to take just rocket bodies from this list, and here's the ranking. Notice in the yellow band at the bottom, the average apogee and perigee is between 800 and 829, roughly 800 and 830. If you look at a distribution of objects on orbit, that's where one of the most pronounced peaks is. And it's exactly what you'd expect. It's crowded. It's a urban intersection. It's a place where bad things can happen. So the general strategy here is that by using this collision rate term, one can calculate a threat value and associate it with every single object on orbit. Then you cull out those objects which are truly debris, like rocket bodies as opposed to payloads. And then you can actually calculate or specify a logical approach to which ones you would remove first. Another interesting thing about this, I haven't illustrated it here because I haven't actually done the calculation yet, but you should be able to take any population against any other population and look at their interaction rates. For example, in January 2007, I think it was, the Chinese blew up one of their old weather satellites, Fenyang 1C. The worst event on orbit in history. 2,500 or so pieces of new debris from that object. You can actually take those LSATs, look at the interaction term between them and all the members of, say, the Iridium constellation. So you can actually assess the threat of population 1 against population 2. I haven't actually done those calculations yet, but you can actually do that between any two sets of populations. It should be straightforward. So in conclusion, the simple PIB model shows there's a threat of catastrophic runaway growth in the orbital debris environment that would not resolve itself for hundreds of years. Although individual small debris objects are currently the most significant threat to individual high-value assets, okay, people do worry about that, the primary threat to the environment in the long term may be argued to be the repository of collective collisional cross-section area resident in large derelict objects such as rocket bodies, since they will be the source of small debris in the future. Removing as few as 2 large objects per month can make a significant difference in the future evolution of the LEO environment. And finally, the collision rate equation can be used as a basis for prioritizing the removal of large objects individually or looking at populations collectively. And this work is dedicated to my 2 sons who have done far more than their fair share of crap duty in Iraq. My son Byron, the one with the big gun, has done 2 tours in Iraq. Aaron, 1 tour, he's out. My son Byron found out yesterday that although he was told he was not going to go to Afghanistan, they are now telling them he is going to go to Afghanistan for tour number 3. And I will not tell you in the terms that come natural to me how I feel about that. But that's just the way it goes. Okay, questions, comments, and remember I probably can't hear you.
How many large objects are we putting up per month?
Well, typically there's on the order of about, depending from year to year, 60 to 80 launches per year. And you're putting up with probably about half of those are putting up something that stays up for more than a year in terms of a significant derelict. Now, some of them will put up an upper stage, it may only stay up 6 months. I don't really count those in my approach, but it's on the order of 20 to 40 per year that stay up there for a long time, you know, where a long time is more than a year.
So the rate of taking out and the rate of putting into orbit is probably pretty equivalent.
Yeah, as long as you, because part of the issue here is removing the large stuff. As you saw back in that thing where the top 10% by size, by number, 1,216 objects, represent 80% of all the cross-sectional area. The rest of them are sort of like neutrinos. Right. Orbital neutrinos. They don't interact with much of anything. Yeah.
I was looking at your equation you had. The n dot equals a plus bn plus cn squared. Mm-hmm. And the first thing that popped in my mind was just a power law model. Just kind of that idea that you can pretty much model anything with a power law or any function with it. And looks like it holds here.
Yeah, it does. And in fact, this particular, there's actually a name for this particular equation besides the quadratic equation in terms of modeling populations. But one place you'll find it is in predator-prey problems. Like I say, you know, wolves and population of wolves and population of rabbits. Rabbit population grows, wolf population grows, they eat too many rabbits, the wolf population diminishes, that kind of thing. Very similar type of equation holds true in population growth, other types of population growth and decay. In fact, one area that I thought would be kind of fun to look at, although the Center for Disease Control probably has much better models than I would even think of putting together, is do something like this type of model for the spread of a virus, things of that nature, looking at different populations, interaction cross-sections between contagious people and an uninfected population, that kind of thing. It would actually lend itself very much to the same type of approach. Anyway, other questions?
That simplified model you created overnight, did the hotel confirm the results of the more complicated model?
As a matter of fact, it did. As a matter of fact, and much to my relief, because these are the people that I worked for, and I really didn't want to, because I'm sure they would have said that this, my model was a piece of junk. But qualitatively, the behaviors are very much the same. And in terms of gross predictions, there's a tremendous consistency right now between the models that people have done that have been developed independently. The Europeans, there's a group in Germany. They have a model called Chain. The Italians, I forget what they call their model. My model and the default NASA models that everybody refers to, every single one of them, number one, identifies the fact that the environment is currently unstable. Number two, that one of the best things you can do is remove the target area. That's why the DARPA and NASA co-sponsored that meeting. Yeah.
So what are some of the ideas that folks in the industry have for actually removing the debris that you prioritize?
Oh, they got all kinds of wild-ass ideas. The thing of it is that that's one thing that came out of this meeting. People were actually presenting different concepts for in-space garbage collection or removal, where you go up and attach some type of little deorbit burn module on something. But there's no consensus at this time as to what the best approach is, bottom line. On top of that, there's also some cranky little legal issues. Suppose there's a Russian rocket body that I or somebody else say, that's got to be removed. Russia says, yeah, well, that's my rocket body. I don't want it removed. You say, well, it's not doing anybody any good. Yeah, well, it's my rocket body. I don't want it removed. So what do? Go say, listen, the rest of us want it removed, so we're removing it. There's some issues. Definitely before we start doing wholesale removal of even just derelict objects, everybody could probably, sensible people could agree are indeed derelicts. There will have to be treaties put in place and some type of international oversight as to how this sort of thing gets done, which means it will complicate what would otherwise be a fairly simple thing to do. Yeah?
Do they accept liability if it wrecks somebody else's property?
Yeah, see, the liability issue comes in, and nobody wants to accept liability for anything.
If you don't accept liability, then you'll have no claim to say, leave it up there.
Yeah, that's an interesting point. There are a bunch of sticky issues like that people who, non-science people whose whole world is politics and bureaucracy, are going to probably have to sort out and take an inordinate amount of time to do it. Yeah.
The first question kind of hit on this a little bit, but how many of the rockets that are, or the launch vehicles that are launched per year, how many have a controlled reentry, so people are taking care to deorbit what they've now used and are done with?
I don't know an exact number, but I think that a good answer is very few are actually really well controlled. Because if you go to there is a website called SpaceTrack. You actually have to get an account. You have to have some justification for having an account. It's usually pretty easy, like, I work in the aerospace industry. I sure would like to have an account. At least at the moment, it's pretty easy to get one. But you can go to their prediction page, and you can see what's predicted to decay in the next 30 or 60 days. And there'll typically be rocket bodies and large articles, and it's very clear that there's nobody controlling them. They're just going to come in. That's another theorem. The oceans are big and will absorb almost everything. Yeah.
Point, I'm not even sure you can answer this, but at what point is this really a problem of economic cost, some sort of cost versus benefit curve? It becomes cost effective to go up there and remove something versus just putting up with the insurance cost of trying to mitigate a loss.
That's an interesting question. There was one whole afternoon session dedicated to just issues like that at this particular meeting. There were actually representatives from a couple of insurance companies that insure payloads and things of that nature, talking about exactly those sorts of things. I have to admit I wandered out during those sessions. But cost effectiveness is a real consideration. I mean, if it's going to cost $1 billion a year to police the environment, and it can clearly be shown that, yeah, sure, you'd take some hits, but they're on the order of $400 million a year, somebody's going to say it's not worth the trouble yet. But the problem of it is the way we're populating the environment with large pieces of debris, we're basically buying a future problem. By the time it does become cost effective, the problem could be beyond our capacity to make a significant impact. In other words, we could be up on that part of the curve where the population is growing so rapidly that instead of 2 objects a month, we'd have to remove 4 or 8 or 15 a month. And so then the costs go up because we didn't do anything earlier. But anyway, yeah.
You've ignored extraterrestrial sources of debris calculations I'm mentioning. The odd meteorite coming in, it just doesn't count. Does it start to become a problem when you really get these takeoff conditions and things be stable and we've now got large pieces of ice coming in and colliding?
Actually, for example, if you take a look at some of the NASA publications, they present everything in terms of flux curves as a function of size, number of hits per unit time per unit meter, number of hits per year per square meter of target area. The meteoric debris, the natural environment is not as significant as what we've done to ourselves in the regime from roughly 200 to 2,000 kilometers. The trash we've put up there way dominates our concerns.
But we're in a nonlinear, unstable potential, right, where it could become a problem, or is it just so far out of the curve right now, we don't have to worry about it at all?
Well, of course, the natural environmental flux remains fairly constant regardless of what we're doing. But as far as looking at as we increase the number of objects, of course the cross-sectional area is not increasing as rapidly. I don't know. It would require some further looking into. I probably cannot give you a real good answer off the top of my head that I'd be able to say tomorrow morning that was the right answer. Okay, anything else? Yeah.
What are the future implications of all these multi-satellite systems we're putting up, like GPS, every country putting up their own system for security reasons?
Yeah.
What direction are we headed in there?
The implication, as far as I'm concerned, is that we're becoming way too dependent on these systems. I've written another paper that I presented at a AIAA meeting, AAS meeting, American Astronautical Society meeting in January of last year in Galveston, looking at space warfare scenarios. If the militaries of the world decide that going after each other's constellations is a smart thing to do, as few as 25 to 50 satellite disintegrations basically would produce an environment that's not useful to anybody for about 800 to 1,200 years. And the problem with that is, number one, we wouldn't be able to use an environment everybody needs. Number two, since everybody is so dependent on it as it stands right now, you have some significant problems. I mean, in international commerce, just buying gas at the gas pump, you could run your credit card, but it doesn't get transmitted anywhere. One of the things that scares me a little bit is, suppose you have a nation like the United States, which is extremely dependent upon these constellations like GPS and weather satellites and communication satellites and satellites that transmit commerce, international trade. And then you have a nation that just barely has a space capability. And they're not necessarily real dependent on the same systems we are. Then they're in a position to do something fairly primitive and simple, like putting up just the right amount of debris or trash, or even using microsats or minisats to latch on to key elements of various systems like parasites, and on a given signal on a given afternoon, take out all of our stuff, or at least enough of it to totally disrupt our economy, and yet really not hurt themselves. And see, such nations, who might they be? Anyway, that's a potentially dangerous thing. Yeah?
As an astronomer, what's the danger of, say, a coronal mass ejection wiping out all of our satellites anyway?
Yeah, that's a real possibility. If we have sufficient warning, I believe a number of the systems can be safed, but without sufficient warning, or without systems that had any kind of protection capability designed into them, we could be in for a real shock at the next solar peak if we just happen to get a really whopping good CME headed our direction. Surely somebody has modeled that by now, but I haven't. Being a galactic and intergalactic guy, I haven't been keeping up on the sun too much until just lately. I have a little widget on my computer, and I've noticed lately the sun's been starting to get more active. Any other questions, comments, insights, disputes? Okay.
All right. Thank you.
Thank you very much.